Yes, good morning, one and all. So today I will be discussing about the broadband wireless channel fading. Okay. So in the previous class, we have discussed about path loss and as well as the shadowing, if I am correct. Is it right? Yes, you people have remembered what I discussed in the previous class. I said I have discussed about path loss and shadowing effects. Is it possible to say any one of you path loss occurs due to what? Yes, the path loss happens due to what I'm asking. Yes, Ashwin Kumar, can I expect you to say something about path loss? Ashwin. Yes, Ashwin. No response. What about Madhura? Madhura. So Madhura also noted there. Yes, what about
Sir,
Ritika?
yes, sir.
Hmm.
Yes, sir.
You see, I asked a question. Is it possible to say a
Path,
few words
yes,
about
sir.
path loss? Yeah.
Like pathless occurs due to free space loss and refraction, and when there is a coupling loss, medium coupling loss.
First of all, first thing you are not telling. Path loss is due to what? It is mainly due to what? Path loss. Yes. Yes. Any one of you need not be Madhura. Others can also. Yes. What about Pranav?
Sure.
Path loss happens due to what, man?
So, like due to the increase in distance between the main transmitter and the receiver, sir.
Yeah. Very good. We were able to see this slide.
Yes, sir.
Yeah. I
Yes.
expected this. Okay. So I said path loss is due to distance. Okay. Is due to the distance between the transmitter and the receiver. And we all know what is the formula for free space path loss. Okay, it is also known as Friss formula. What is that? Any one of you can say free space path loss formula, or it is also known as Friss formula. Yes, quickly, it is there here. So the received power will be equal to what? The transmitted power into gain of the transmitting antenna and gain of the receiving antenna to lambda by 4 pi d whole square. Okay. So in case of free space, the received signal power depends on the wavelength of the signal. Okay, it is directly proportional to the wavelength of the signal, or I can say it is indirectly proportional to the frequency of the signal. Okay, because lambda is equal to c by f, right? So it is inversely proportional to square of the frequency of the signal, and as well as the distance between the transmitter and the receiver, right? And as I said, what is the two-ray approximation model? Usually, we need to consider the terrestrial propagation, right? So, which is not a free space. The two-ray approximation model is this. So, in that case, we write the expression for the received power is what? PR is equal to PT into GT, GR, H square T, H square R divided by D power 4. So, here the received signal power depends on the transmitted power, transmitted signal power, then uh, gain of the transmitting antenna, gain of the receiving antenna, and as well as the height of the transmitting and receiving antennas. And it is inversely proportional to what? D power 4. Okay, D power 4. So here the frequency or wavelength of the signal will not come into a picture. in this case. Okay, in case of two-ray approximation. Okay, so here the distance dependency is more. So energy loss is more severe with distance in a terrestrial system than in the free space, I said, right? Then I told about the empirical formula by considering different propagation environments. What is that? Expression for path loss by using empirical formula, that is received power is equal to Pt into P naught into D naught by D to the power of alpha, where alpha is the propagation path loss exponent, I said, and P naught is the average received power at a distance D naught, right? So D naught, usually we consider that as a reference distance, which is equal to 1 meter, right? So where D is the distance between the transmitter and the receiver. Okay. Then I told, I think even I discussed about the problem also, right? How the path loss exponent plays an important role about the signal to interference ratio, right? If it is large, what happens? If it is small, what happens? So if the path loss exponent is large, then the signal to interference ratio will be improved, right? So I have taken an example with a different number of interfering base stations with respect to the desired base station at different distances, right? With 1 kilometer, some number of interfering base stations, with 2 kilometers, some other number of interfering base stations, and with 10 and with 4 kilometer of distance, some other, I think around I consider 10 interfering base stations. So with that, I could calculate what is the signal to interference ratio for two values of path loss exponent, that is when alpha is equal to 3 and when alpha is equal to 5 is what. Then I discussed about the shadowing. Basically, I said shadowing happens due to the obstacles, right, of objects between the transmitter and the receiver. So it may be due to the big buildings, right? So the electromagnetic signal has to pass through that, right? So due to that, I said the shadowing will happen. Is that fine?
Yes, sir.
Yeah. Yes, I was telling now, shadowing happens due to the what? Buildings between the transmitter and the receiver, right? So here we take the variation of the received signal strength, right? I said due to obstacles. Those obstacles may be trees or buildings located between the transmitter and the receiver. So we introduce that effect as the random effect, and we call that as a shadowing. And I've given the expression for shadowing, and this is the empirical path loss formula for shadowing. That is, the received power is equal to transmitted signal power into P naught, and this is the symbol we use for saying it is a random process, shadowing random process. Okay, and D naught by D to the power of alpha. So compared to the empirical path loss formula, what we have discussed for this considering all environments, right? So this variable is added here. There is a shadowing random process. I think that I shown in this diagram, right? Yeah, received power is equal to Pt P naught into D naught by D to the power of alpha. So this is for different propagation environment. This is the empirical path loss formula, right? And what is added in case of shadowing? One more, the variable which is called shadowing random process, right? So we can model the received power as a random process. So because of that, we think in case of path loss, that is basically due to distance, right? Distance between the transmitter and receiver. That is the loss happens at the received signal, right? So that we think as mean or expected value of the received power. Okay. Path loss, we can think that it is the mean or expected value of the received power, and this shadowing, okay, can be think of what, because it is due to the this shadowing happens due to perturbations from expected value, right? So as I said, shadowing happens due to macroscopic objects, right? And it has a correlation distance. It will be in the order of meters or tens of meters. Okay. Hence, we can consider this shadowing is all means the alternative name for shadowing is known as the large scale fading, we say. Okay. So here I have given a graph of what received signal power. Hope you are able to see this slide. Yeah. So received signal power. So this graph is about two things. One is the path loss. I said no, path loss. What is the received signal power? That is in terms of dBm. What is shown in y-axis, and x-axis is the distance. Okay, and it is a logarithmic scale you have taken. And this just one line, no, dotted line, what I have shown, that is the path loss. So as I said, the distance trend in the path loss can be thought as mean or expected value of the received power. And with respect to that received power, that mean value, so there is a variation in the signal power, right, as the distance increases. That variations, we call that as a shadowing. Okay, that is due to shadow fading, we call. Hope this point is clear. We
Yes, sir.
consider path loss as the mean of the received power, and shadowing is the what? Variations with respect to that mean value. Okay, in the received signal. Fine. So this graph is important. You should be able to write with respect to this graph all these things. Okay, path loss is the mean or average or expected value of the received power, and shadowing is variations from that mean value. Okay, fine. And okay, just okay. This is the slide where okay, I think I will come back to this. Yeah, is it changed? The slide is changed. Hello.
Yes, sir.
Now I am in which slide? Is it possible to say?
Introduction to
radio wave.
Okay, introduction is not changed. Okay, 1 minute. Yeah, I think I told about this now in continuation with the shadowing. Have I discussed about this slide in the previous class? I said no, shadowing value, which is denoted by the symbol, is modeled as log normal random variable. Okay, shadowing is log normal. Okay, that is why I've taken x-axis distance as logarithmic scale. Okay, and the value of that x, right, that is the log normal random variable, will be written as 10 power x by 10, where the value of x is n of 0 comma sigma square x. So this n of 0 comma sigma square s is the what? Gaussian distribution with mean 0 and variance sigma square s. Okay, we consider this as what? A Gaussian distribution. I hope you are all aware of different distributions. Gaussian distribution, Bayesian distribution is there, then Poisson distribution and other things, right? So we consider this as a Gaussian distribution with mean 0 and variance as sigma square s. And this standard deviation, that is sigma s, will be expressed in terms of dB, and the value of that standard deviation will be in this range, 6 to 12 dB. Okay. So what I wanted to say here is shadowing is an important effect in wireless networks because it causes the received signal to interference noise ratio to vary dramatically over long time scales. Okay, shadowing is an important effect in wireless networks because it causes the received signal to interference noise ratio to vary dramatically over long time scales. When we are deploying the system, right? So the system design and the base station deployment must account for this log normal shadowing, either through this macro diversity, okay, then variable transmit power, and or by simply accepting that some users will experience poor performance at certain percentage of locations. I hope you all understand these terms because you might have experienced uh, even in our institute only, you may get better signal at some point of places. Okay, you may not get the coverage of a signal if you go to some other parts of the building, right? So that is all due to the shadowing effect. What I wanted to say is here. Okay. So why it is log normal? Even for that also there is a reason. Okay, just find out why shadowing is log normal. Okay. Then so with those two things, one is path loss, another one is shadowing. Okay, these two are what I can say is belongs to large scale fading. Just now I said no, shadowing is alternatively called as a large scale fading, right? So that is basically due to distance. Okay, these two, path loss and as well as shadowing, are due to distances, right? One is yes, what I said, path loss is due to distance, and as well as the shadowing is due to uh, objects between transmitter and receiver, right? And what type of objects it is? Macroscopic objects, that is big buildings, trees, and all, right? And even if the distance between transmitter and receiver is in the order of tens or hundreds of meters, right? That is why it is categorized as, means here I have given a overall fading types. Okay, usually we classify these fading types as two things. One is large scale fading, another one is small scale fading. Under large scale fading, we say two types. One is path loss, another is shadowing. So this is due to, I said, these two under distance, right? One is due to distance, one is due to obstructions between the buildings, between the transmitter and receiver due to macroscopic or macro objects, right? Another is small scale fading. In that, again, we classify that as fast fading, slow fading, then multipath fading. Under multipath fading, these are the two types. One is flat fading, another is selective fading. Okay, so I hope you will be able to understand. These are all important things which you need to understand. So these are the things which will enable you to understand why we are deciding about the so many parameters while designing a mobile communication system. Okay, means it is all about in-depth study about the channel. Okay. Hope you understand what I'm saying. Yes.
Yes, sir.
Yeah, I think here just it is an again introductory part what I have shown here. So this is what I said, no, PR by PT. I was telling about path loss, right? Versus distance is written here very slow, slow and fast. Three different characteristics variations. So let me take up. I think I discussed about these two, path loss and as well as shadowing. Now let me take up about the other things. Yeah. So broadband wireless channel, I written heading as fading, right? Okay. So far I discussed about the two aspects, right? One is about the path loss, another is about the shadowing. I said those two comes under the category of large scale fading, right? Because path loss happens due to distance and shadowing happens due to the objects between the transmitter and receiver, right? The next one is the fading, we say. So this fading is caused by the reception of multiple versions of the same signal. Okay, multiple versions of the same signal. So for understanding that, here, okay, I will come to this. So here is a transmitter, right? Maybe the receiver is at this point. You may be seeing the different paths, right? I have taken here only two main multipaths. This is one path and this is another path. So the signal receiver is here, right? Even to show you better, let me skip this and I will just go back and show that. I think already I've shown this. Yeah. Mm. Yeah, able to see this? So here is a
Yes, sir.
transmitter, right? And this is the transmitted signal. Transmitted signal. So because so many obstructions are there between, and this is my receiver, right? Traveling in a car, the receiver is here. So it will be taking a different paths, right? So it may be due to reflection, diffraction, scattering, and all other things is written here, right? So at the receiver, what we are seeing the multiple signals, right? This is my transmitted signal. I should receive only this one, right? It is a receiver. But what happens? It takes different paths, no, in the wireless channel. So I will be receiving the same signal at a different intervals of time. Hope you're able to see that multiple versions of the same signal is written one. This is one signal. Then another signal with some delay and with less in magnitude is written. Then another signal with again reduction in the magnitude and as well as some delay. Hope I have shown here three signals. Able to catch this? Yes, able to see this, or is it possible to see? Are you able to see this diagram? I am receiving the same signal multiple times at the receiver. That is due to what? That is due to, because of what? Because of reflection, diffraction, scattering, because it is a wireless channel, so many obstructions will be there between the transmitter and receiver, and it takes multiple paths. So each path may take its own time, right? Depending upon the distance. So I will be receiving multiple versions of the same signal at the receiver. Hope you got this point.
Yes, sir.
This is known as the fading, we say. Okay, this is known as the fading. Okay, and one more picture also is shown here. So this is the receiver, and here is the transmitter with the different colors. Hope to get interest made here. So transmitters is the path 1, is the path and 2, and so on up to path n is written, right? Right. Hope this is the line of sight link, and these are all multipath, means non-line of sight links. Okay, I will come back to this diagram later on. It is not of now to understand. Hope you got this picture. Why we get multiple copies of the same signal at the receiver? That is due to what? Is any one of you can say that is due to what? Yes. Yes, people are not responding. I've shown the diagram. I'm asking why we get the same signal multiple times at the receiver.
Can you repeat it, sir?
I'm
Scattering.
asking why we are receiving the same signal multiple times at the receiver. I think I should go back to that slide only.
So it would have scattered
See,
multiple times, sir. Like same signal.
that is maybe due to multiple paths, right? That may be due to reflection, scattering, right? I hope you all understand this picture. Maybe scattering. So here it is written why, when do we say reflection happens? When do we say diffraction happens? When do we say scattering happens? So scattering is due to what? Foliage, lamp post, street signs, walking pedestrian. Means due to that we say scattering. Diffraction, obstacles with dimensions in order of wavelengths. Okay, that we say diffraction. Reflection, that is due to large buildings and earth surfaces. Due to that, we say reflection happens, right? So here, this is the transmitted signal I said, and the receiver is here, right? So is receiving the same signal multiple times, right? Here more than one I have shown with a different magnitude, and there is a delay also from one signal to another signal. Here I have shown three different signals. Three signals of same type but different in magnitude, and they are arriving at slightly different times, different intervals of time. Maybe one I may be getting at 1 microsecond, another may be at 1.01 microsecond, another may be at 1.02 microsecond, like that you can think. Okay, the same signal I am receiving multiple times. So this, as I said, that is due to because of these things. And since the channel is wireless and it takes multiple paths, so depending upon the distance, I will be receiving the signal, same signal multiple times, right, with a different magnitude and as well as in different times. Fine. So that I said is known as the fading. So now fading is caused by the reception of multiple versions of the same signal, right? So the multiple received versions are due to what I said. It may be due to reflection, scattering, right, diffraction and all. So that are referred as multipath, as shown there, and here also the same diagram is there. So reflections may arrive at very close to the same time. So here I would saying there is a local scattering around the receiver. Okay, if there is a local scattering around the receiver means here there is a receiver, right? So here I have taken two paths. This is one path and this is another path. So I have considered these are the two multi paths. But at the receiver, okay, here I said again there are again multiple paths here, right? So the reflections may arrive at very close to the same time. Okay, if there is a local scattering around the receiver, that is one thing. Another one is the reflections may arrive at relatively longer intervals. Okay, that is due to multiple different paths between the transmitter and receiver. So here two things you need to understand. One is due to local scattering. Okay, so means the reflections may arrive at very close to the same time. Very close to the same time means I think in the previous example I shown the transmitted signal and the multiple received signals. If their time difference is very small from one signal to another signal, okay, that is due to what I say local scattering. Another one is the reflections may arrive at relatively longer intervals. So that is due to what multiple different paths between the transmitter and the receiver. So to understand those two difference, one is I said due to multiple paths between transmitter and receiver, and another one is local scattering. So what is local scattering? Here I have shown. Hope you are able to see this diagram. Local scattering. So here this is a multi-path. So this is one path I am saying, this is another path. So due to multiple paths between the transmitter and receiver, the signal which is going to be received at the receiver may be slightly at longer intervals. Means from one signal to another signal, there will be more gap. Okay, due to local scattering. Okay, that is due to what? I may be able to receive the signal at the same time, very close to same time. Means the time difference of arrival of a signal at the receiver will be very small from one signal to another signal. The same signal will be arriving multiple times. That arrival time will be small. That is due to local scattering, we say. Hope this picture is clear. The channel may have few major paths that we say multipaths, right, with quite different lengths, right? And then receiver may see the number of locally scattered versions of those paths. Yes, hope this is clear. In what way? When we say it is a fading, if I receive multiple versions of the same signal, that is due to the reflections and as well as multiple paths, that I call it as a fading. Okay, so fading means there will be variations in the signal strength, okay, over short interval of time. Okay, that is why it is called small scale fading. Hope are you getting my point?
Yes, sir.
Yeah,
Yes.
see here I classify now fading, large scale fading and small scale fading. Okay, so these are different varieties. I will come to that one by one. Okay, then okay, so let me say about this. Okay, this is the waveform which I wanted to explain how the signal Okay, at the receiver, if it is received from different paths, that is due to reflection, right? It may be means so when I am receiving signal at the receiver from different paths, it undergoes phase shift. Okay, it undergoes phase shift. Uh, if the phase difference is large, okay, so I say it is an interference, right? It may be a constructive interference or it may be a destructive interference. So it all depends on how much phase difference is there between those two received signals. And here two diagrams I have shown. One is the first one is the constructive. It is due to the constructive interference. Okay, because so able to see the two signals. One is x1 of t, or small dot. Another one is the x2 of t, is another signal, right? And here able to see that phase difference. How much phase difference we are able to see? Here the phase difference is large. So due to that, I am getting the constructive signal. Means the amplitude of the received signal y of t will be equal to x1 of t plus x2 of t is written here. Yes, of course, the amplitude of the received signal is more. Okay, because the phase difference between these two signals are more. And another one I have shown here. So this is one signal, right? X1 of t, and this is another signal, x2 of t. And here I say it is a destructive interference. See, the amplitude of the received signal is not that much, right? So it is a destructive interference, I say. Hope you are able to understand what I am talking, all of you. Here the phase difference is small. Yes, I need response. Are you able to understand what I am saying?
Sir, your voice is breaking, sir.
Huh? What is? Oh, my voice is breaking. Yeah, is it now? Hello?
It's fine, sir.
It's fine. Yeah, what I said is, see here two signals are there, right? X1 of t and x2 of t. If the phase difference, see x1 of t is coming from one path and x2 of t is coming from another path. Okay. If the phase difference between those two signals is large, then it will be an constructive interference. So constructive interference means the amplitude of the received signal will be more. Okay, the amplitude of the received signal will be more. That is why it is shown with a thick or dark line with more magnitude. Okay, the second case is here also I have two signals, x1 of t and x2 of t. The phase difference between those two received signals is small. Okay, because of that, it is a destructive interference, what I can say, because the amplitude of the received signal is small here. Able to understand this, I am asking. If the phase difference between the two signals which are arriving at the receiver from two different paths, if it is large, okay, then I say it is a constructive interference. In that case, I will be getting the received signal with a magnitude which is larger. Okay, that is why it is called as a constructive interference. When the phase difference between the two signals which are arriving at the receiver is small, then that will be what? Destructive interference. In that case, the received signal amplitude will be less. So, due to reflection, okay, due to reflection, the received signal amplitude varies, right? It may be more or it may be less. That depends on what? That depends on the phase difference between the arrival of those signals, right? Hope got my point?
Yes, sir.
Yeah. So these are all important. That is why I'm stressing. Okay. So that only I said here, and yeah, hope we are able to see this theory. Already I told what is that, right? So depending on the phase difference between the arriving signals, I said the interference can be either constructive or it is destructive, right? so which causes a very large difference in the amplitude of the received signal, right? Even over a short distance, as I said. Means what I mean to say is, see, moving the transmitter or receiver even a very short distance can have a dramatic effect on the received amplitude, even though if we neglect the effect of path loss and shadowing. Okay, even though the path loss and shadowing effects, if they are not changing, even if the transmitter or receiver changes over a very short distance due to this reflection, right? So there will be a large change in the received signal amplitude. Okay, so to make that discussion, whatever I am saying, right? Due to the reflection, there will be an constructive or destructive interference. That depends on the phase difference between the received signal, I said, right? So we can already I discussed about this. I said the channel can be modeled as a time varying channel, right? And I said it will be described as tapped delay line model. Hope you remember. I think I discussed this in the previous class. Tapped delay line model, and I wrote what is the impulse response of that tapped delay line model. That is h of t comma tau, right? Okay. Here, with respect to that, okay, the impulse response of the channel will be h of t, because as I said, if we consider that the transmitter or receiver will be more relative to each other, then I said the impulse response of that is h of t. That will also change with time and as well as with a delay. So I can consider it is a two dimension. Here two dimensions are what? One is delay dimension, which is denoted by tau, and another one is time dimension t. Okay, means the impulse response of the channel changes over distance. What I wanted to say. So when it is changing over distance, it also changes with the time also. Okay. Hope understanding my point. The impulse response of the channel changes with the distance and as well as changes with time. Okay. So to understand the effect of this, right, we need to go for the statistical methods. That statistical method is what? That is for modeling the broadband fading channel is about autocorrelation function. So that autocorrelation function is defined as like this, that is a of delta tau comma delta t. So delta tau is what I said, it is a tau is the delay, right? And t is the time. So change in distance and change in time. So due to that, there will be a change in the impulse response of the channel. So how do I define that? So this is what the definition of the autocorrelation function, which is basically a statistical method, what I said. So a of delta tau comma delta t means change in distance and change in time, right? It is an what? Expected value of h of tau1 comma t1 and complex conjugate of h of tau2 comma t2. Means this is what? Tau1 is a delay and t1 is a time t1, right? Means, okay, just have a look of these three relations. First I consider tau1 t1, tau2 t2, then I wrote tau1 t, then tau2 t plus delta t. Means here there is a change in time, second case, right? And third case is both delay, that is distance, and as well as time are changing with respect to one and another. So I will show the effect of that in the next slide, how it is the channel response is varying with respect to time. Hope you're able to see this diagram.
Yes, sir.
Yes, able to see this diagram. So this is the impulse response of the channel. Okay, this is a time tau comma t. This is the impulse response of the channels. I said no, h0, h1, h2, and so on up to hv. Okay, so h of tau comma t versus tau, right? So this is a different intervals of symbol interval. So these are the different values of h0, h1, h2, and this is what h of tau comma t plus delta t means. Here I'm showing with respect to change in time. Okay, so here you are able to find the difference, no? So h0 is means the magnitude is different, right? So H0, H1, H2 and so on. Yes, able to see at different values of TS, 2TS, 3TS and all. Yes, able to find the difference. As time changes, there is a change in the impulse response of the channel also. This is what I wanted to say. So the delay corresponds to how long the channel impulse response lasts. Then since I said channel is time varying, right? So the channel impulse response is also a function of time. And here I have shown the two responses. One is h of tau comma t, and another h of t comma tau comma t plus delta t. Means the impulse response of the channel at a time t will be different at a time t plus delta t. What I wanted to convey here is, okay, at a time t and as well as at time t plus delta t. So t plus delta t means there is a change in time, right? Because it is a time varying. So channel is time varying, hence its impulse response will also change. Let's hope this picture is clear.
Yes.
Able to find the variations in the value of H0, H1, H2 and so on. See, magnitude is different, right? Here H0 is this much value and H1 is reduced, right? Obviously, I can say it is time varying. So impulse response of the channel is also changes. Okay. So how do we model? I said, so we use the statistical method that is known as the autocorrelation, right? So visually we consider that as what? Wide sense stationary. Okay, we assume the channel response is wide sense stationary. Means the autocorrelation function only depends on delta t, that is t2 minus t1 we say. That is in the first step what I wrote, I think here. So tau1 t1, tau2 t2, right? T2 minus t1 is a delta t. There is a change in time. Okay, fine. So in the second step, what is shown here? Tau1 t, then tau2 t plus delta t, right? So what I mean to say is, in the second step, we assume that the channel response by considering different paths. Okay, response of paths arriving at different times, tau1 and tau2. They are uncorrelated. Okay, that allows the dependence on specific times, tau1 and tau2, will be replaced by simply tau. Then the channel can be described by that autocorrelation function, whatever I have shown there, and that we call it as a wide sense stationary uncorrelated scattering. Okay, WSSUS, that is wide sense stationary uncorrelated scattering. So this is one of the most popular model, okay, which is used for wideband fading channels, and we say it is quite accurate also. Okay, fine. So with this basic understanding, okay, how the channel response varies with channel impulse response varies with the time and as well as varies with the distance, right? I said it is different at different intervals of time. We need to understand some important parameters uh, based on that autocorrelation function model. What I said, it is a wide sense stationary uncorrelated scattering model, right? So that autocorrelation function will explain the key wireless channel parameters. Okay, let us see what are those key wireless channel parameters. Yeah, I will say the definition of these things in the coming slides, but let me just say if these parameters are large, what happens? If these parameters are small, what happens? And how does it affect the, or what is the impact of these parameters on the LTE design? Yes, able to see the table?
Yes, sir.
Yeah, able to read also?
It's a bit small, sir.
It is a bit small. Okay, I will read. So I said, no, what are the key channel parameters, right? So one is the delay spread. Okay, delay spread, which is denoted by tau. Okay. I think two things I told in the previous class. One is coherence time, I think I talked, and even delay spread also. I will come to this. What is delay spread? How do we define? Already you are aware, but you don't know. This is what this is what is called as delay spread. I will tell that. Okay. So first parameter, our first quantity, what I wanted to say is the delay spread, which is denoted as tau. Okay. If the value of this delay spread is large, okay, larger than what? The symbol duration. So capital T is the symbol duration. Okay, if this delay spread is much greater than the symbol duration, then we say it is a frequency selective. Okay, that effect is frequency selective. Okay, if the delay spread is much smaller than the symbol duration, then we say it is called frequency flat. Okay, so when do we say it is a frequency selective fading, and when do we say it is a frequency flat fading, will be described by the value of delay spread with respect to the symbol duration or bit duration, what I can say. Hope it is clear. Yes, I am asking, is it clear? Delay spread. I have not yet defined what is delay spread. Just I am saying, if it is larger than the symbol duration, then we call it as a frequency selective. If I use a word frequency selective fading, then it should come to your mind that, okay, delay spread is much greater than the symbol duration. Okay, fine. Then if the delay spread is much smaller than the symbol duration, then I say it is a frequency flat fading. Okay, so how does the value of this delay spread, okay, impact the design on LTE, right? So the larger the delay spread, okay, relative to the symbol time, what happens? If the delay spread is larger, okay, compared to the symbol time, what happens? The inter-symbol interference will be more. Hope you are able to get this idea. If the delay spread is larger than the symbol duration, okay, then the inter-symbol interference will be more, I can say, or the inter-symbol interference will be severe. And okay, so even I can say what is delay spread. So delay spread, I will come back to that. I will just tell first what is delay spread. Okay. Yes, able to see this slide? I said no, delay spread. It is defined as what? So I have shown here, right? It is a transmitter, and there will be, and here is my receiver, right? So due to various objects between the transmitter and receiver, and there are multiple paths also, right? And this is my transmitted signal, and the same signal I will be receiving at the receiver at different intervals of time with a different magnitude, because that is due to what I said, because the channel is time varying, right? So there will be change in the impulse response of the channel. So because of that, there will be variations in the magnitude of the received signal also. So because there will be attenuation, right? Hope you are able to understand this point. So I have three paths. One I can say A, this is B, and this is C, right? This is my signal which I am going to transmit at the transmitter side. So which I am going to receive at the receiver slightly at different intervals of time. Okay. So from path A, I am receiving at time t minus t1. Then at through path B, I am receiving the same signal with a different magnitude at time t minus t2. Then through path C, I am receiving the same signal at a time t minus t3 with a different magnitude. Okay. So why I receive the same signal with different magnitude? I said that is due to because of reflection, right? Even shadowing, even due to scattering, right? Because there will be a loss in the signal. So I will be receiving the same signal, right? Right. So this is the echo of the signal, no? At a different intervals of time, I say. So the time difference between the first received signal and the last received signal, that time difference is known as the delay spread, we say. Hope you got my point. Due to multipath, each symbol transmitted by the transmitter, right, is received multiple times at the receiver, right? This creates an impact of an echo, right? The duration of the echo is called the delay spread. Yes, hope you could understand what is delay spread.
Yes, sir.
Yes,
Yeah.
sir.
What I wanted to say is, due to multipath, each symbol transmitted by the transmitter is received multiple times at the receiver. That creates an impact of an echo. The duration of the echo is known as the delay spread, right? So in an urban environment, the delay spread may be in the magnitude of 5 to 10 microseconds. In urban areas it is, okay? In an urban environment, this delay spread will be at what magnitude I said? It will be the magnitude of 5 to 10 microseconds. Now, what I said, if the delay spread, okay, is larger than the symbol duration, I said what? It is a, yes, hope this point is clear. At least delay spread. I will go back to that slide.
Yes, sir.
Yeah. Okay. After understanding what is delay spread, let me say about the impact of that, right? I said if the delay spread is larger than the symbol duration, hope you are able to visualize that what is delay spread. And if that delay spread is more than the symbol duration, I said it is a frequency selective, right? If the delay spread is lesser than the symbol duration, then I said it is a frequency flat. So what happens, I said, how does it impact on LTE design? So larger the delay spread, right, when compared to the symbol duration, what happens, I said, there will be more inter-symbol interference. So inter-symbol interference is what? Overlap of the present symbol with the previous symbol, right? So that leads to inter-symbol interference. Hope this point is clear. How delay spread plays an important role in the design of an LTE.
Yes, sir.
Yeah. So the next quantity is coherence bandwidth. Okay. So coherence bandwidth is denoted by BC. Okay. So inverse of coherence bandwidth means if 1 by BC, I'm saying here, right? 1 by BC. I said coherence bandwidth will be denoted by BC. Let me tell the definition of coherence bandwidth also. Then I will come to this slide. How does it affects the LTE design, right? If it is large or if it is smaller than the symbol duration, what happens? Is that fine? Yes, my dear students, you should respond. Is that fine? If I say then and there, what is what? Then if it is larger than symbol duration, what happens? If it is smaller than the symbol duration, what happens? How does it impact on LTE design? If I say like that, is that fine? Means that you will be able to correlate quickly. Okay. Yeah. Just yeah. With this slide, I think I will be able to explain what is coherence bandwidth. Yeah. Yeah. Yes. Able to see this slide now? Coherence bandwidth.
Yes.
Yeah. So coherence bandwidth is the what? Range of frequencies over which the channel can be considered flat. Okay. It is defined as what? The range of frequencies over which the channel can be considered flat. Means what? Means there will be no variations in the impulse response of the channel. Okay. Over what range of frequencies there will be no variations in the impulse response of the channel, no? That we call it as a coherence bandwidth. So to understand better, here I have taken an example. Okay. That is, the channel passes all spectral components with equal gain and linear phase. Right? If it is flat, okay, right? So it will be passing all the spectral components with equal gain and linear phase. Okay, I will not tell about about delay spread. So it is a function of RMS delay spread. I will come back to that. So here for understanding, so two paths I have considered here, right? Multipath channel. So I have sending two sinusoids with frequency separation, right, which is greater than the coherence bandwidth, right, which is greater than the coherence bandwidth, are affected differently by the channel. I mean, this is one sinusoid having frequency f1, and this is another sinusoid having frequency f2. If the frequency separation, okay, right, two sinusoids with frequency separation greater than the coherence bandwidth, right, then at the receiver, each of these signals will be affected differently by the channel. Okay. Hope you got this point. Coherence bandwidth. Yes, you people should say yes or no. So it is the range of frequencies over which the channel can be considered flat. Have you got my point? So over what range of frequency the channel impulse response is constant? Means if I means the output of the channel should provide equal magnitude signal. Okay, if I give an input of say 2-3 impulses having a magnitude of 1 volt, okay, the output of that channel should be of 1 volt, okay, over certain range of frequencies. Then I say it is in the within the coherence bandwidth. Yes, are you able to understand this concept, coherence bandwidth? Yes, I'm not able to hear. Somebody is saying something, I could not hear it. Are you able to hear my voice?
Yes, sir.
Yeah. So coherence bandwidth, I repeat once again, it is a what? Range of frequencies over which the channel can be considered as flat, right? I said the channel passes all spectral components with equal gain and linear phase. So for an example, here I have considered two sinusoids, right, with frequency separation which is greater than the coherence bandwidth, right? And I am saying, and these are two sinusoids coming from two different paths, okay? If their frequency separation is greater than the coherence bandwidth, then these two signals will be affected by that channel differently. Okay, so if they are within the coherence bandwidth, then they would have been received at the output of the channel with the same gain and same phase also. Okay, so now let us try to understand the importance of this coherence bandwidth in the LTE design. I said no, if it is large, what happens? If it is small, what happens? With respect to the symbol duration. Yeah. Yeah, if the coherence bandwidth, right, if the coherence bandwidth is smaller than the symbol duration, then we say it's a frequency flat. If the coherence bandwidth is greater than the symbol duration, then we say it's a frequency selective. So this coherence bandwidth, okay, provides a guideline to the subcarrier width. So here in OFDM, in LTE, we use OFDM as a modulation technique, right? And here there are subcarriers. So what is the spacing between each subcarrier? Okay, so that is here taken it as 15 kilohertz. So that will be decided by based on this coherence bandwidth. Okay, so the subcarrier spacing will be usually 1/10 of the coherence bandwidth, we say. Okay, so with this, I think we'll stop for today's class. Let me continue in the 5th hour I have, right? Yes or no?
Yes, sir.
Yes.
Yeah, I will come back to this again in 5th hour. So don't leave. I will take the attendance.